We are going to talk about a pretty neat topic today, which is geologic time, basically looking at the history of the Earth through the use of rocks. Because we already know that geology means study of Earth's rocks. So geologic time is looking at things like fossils or the actual rocks themselves to figure out general order of events of Earth's history. So first, when we're talking about geologic time, we need to talk about the divisions of time. So like we divide time into things like decades, years, months, weeks, days. So in geologic time, they do the same thing. They divide it into big chunks of time called eons, smaller chunks called eras, then periods, and then epochs. Now epochs, if you notice in the picture, are only found in that most recent era, the Cenozoic era. And that's because that's the only time period that we can get specific enough information to actually divide it into those chunks of time. It's kind of like if I said, hey, what TV show did you watch 3 days ago? You might be able to figure that out. But if I said, hey, what TV show did you watch on March 12th, 2009? That gets a little more difficult. So we only divide the most recent time period into those little chunks of information called epochs. So let's talk first of all about the big chunks of time, those eons, like billion years, what's happening in those different billion years. So first of all, the first eon is called the Hadean eon, or sometimes it's called the pre-Archean, basically everything that happened before the Archean. Now, Earth did have solid crust then, but we don't have those rocks on our planet anymore. They've all weathered and eroded away. So that 4.6 billion years that most scientists think the Earth is based off of information from other pieces of space. So whether we've had like an asteroid hit us or going and getting rocks from the moon, that's kind of how we figured out that general age. The Earth also had oceans during that time, an atmosphere, but the atmosphere didn't have oxygen. So it was a very different looking planet than what it is today. During the Archean eon, that's when Earth's layers started forming, so the crust, the mantle, the core. It's also when the landmass that is currently North America formed. In fact, we actually live on some of the oldest rocks found on this planet. In the Proterozoic eon, that's when we had oxygen first pop up in the atmosphere. So think about what that meant for life on Earth during that time period. And then all the land masses that were on Earth came together to make our first supercontinent called Rodinia. Then we have the Phanerozoic. That's the eon that we live in now. And I'm going to talk more about that one in the next couple of slides. So one thing to be careful with when you're looking at geologic time scales is how they squish the time. So those 3 eons that I just talked about are in the pink down here at the bottom, but look at your time scale. So Precambrian time, everything prior to the Phanerozoic eon, actually makes up 90% of Earth's history, like roughly 4 billion years. So be careful when you're looking at these time scales because it'll give you kind of a false sense of how the time is divided up. So then we go into Earth's different eras of the current eon, the Phanerozoic. So they're all named for type of life. So the old life is Paleozoic, the middle life is called Mesozoic, and the most recent life is called the Cenozoic. So during the Paleozoic era, Earth was covered in a lot more water, including North Carolina. We actually were not above sea level at all. So oceanfront property pretty much started in Tennessee. Then there was another supercontinent called Pannotia, and it was mostly centered around the southern hemisphere. You can kind of see there where it comes together at the South Pole in the picture. That broke apart, and then later in the era, the land masses came together again, forming the Appalachian Mountains, which are super old. They're like over 200 million years old. So they're some of the oldest rocks here on Earth, and then forming into a supercontinent you may be familiar with, Pangaea. Now, in the Mesozoic era, that's when Pangea started to break apart. And as South America separated from Africa, as North America separated from Asia and Europe, that's when the Atlantic Ocean formed in between those land masses. Now, what separates the Mesozoic era from our current era, the Cenozoic, is that mass extinction 65 million years ago, including the mass extinction of the dinosaurs. So everything since the dinosaurs, including the most recent ice age, including current time, goes into that Cenozoic era. So how in the world do we know all this stuff? I said, oh, it's geologic time and we know it from the rocks. So I can't go way in depth with it, but I do want to share just a couple of ways that they know this stuff. So the first thing is called relative dating. We can't go back and figure out exactly how all of these rocks worked, how old each of these rocks are, but what we can do is put events in order from 1 to 2 to 3 to 4. So there's a couple of different rules that they use to figure this stuff out, and a lot of them are really common sense. So the first one's called original horizontality, and we actually talked about this when we talked about sedimentary rocks forming, that they form in these perfect horizontal layers. So if you come across the rocks where they're not perfectly horizontal, like the picture on the left where it says older, those rocks have twisted and turned, but they started off horizontal. The second rule, superposition, is something we talked about when we talked about your laundry pile, and that the oldest laundry would be at the bottom of your pile and the newest laundry would be on the top. So that's true, it's just this time we're talking about it with rocks. Then we have cross-cutting relationships. Basically what this means is if you see something cutting across those nice horizontal layers, it happened after the layers formed. So the layers are older than the thing that cuts across it. So in the picture on the left, that's an igneous rock that has cut across during that time period. So all those horizontal rocks were formed, and then that igneous rock just said, hey guys, what's going on? And cut across those rock layers. So it's younger than all those other layers. This can also be true if you have a fault line, basically the result of an earthquake. So the picture on the right shows that A used to be beside A, B beside B, C beside C, but then that fault line came and twisted them and shifted them. So A, B, and C existed first, and then the fault line cut across them. So it's younger than A, B, and C. All right, let's see how you're doing with your relative dating. So pause the video, grab a scrap sheet of paper, see if you can put these rock layers in order, and I'll share the results on the next slide. Pause it. Pause that video. All right, how'd you do? Now, if you put C as your oldest rock layer, hold on, I will explain why it's not. So first we have the rock layers D, H, and A. They originally would have been horizontal, but something happened to twist them. Then we have rock layer C, and that is an igneous rock that's kind of come up like a puddle of magma that's come up and cut across those rock layers. C, even though it's on the bottom, is younger than D, H, and A, and we know that because it has cut across them. So they had to exist first before C could cut across it. Then we have the fault line G. And the reason why we know C came before G is if you look at the top little corner right before you get to rock layer F, you can see just a little bit of C, that gray color. So C existed first and then G cut across it. Then we have F, I, and B, and then rock layer E sitting right there on top after all those other layers formed. How'd you do? Did you do good? All right, there's just a couple other pieces of evidence that help put things in order. One of them is, like I mentioned, the Appalachian Mountains are very old and they are very similar to some rocks that we find in Europe. So not only are they similar in age, they're similar in rock type. So we kind of can start to piece together that when those mountains formed, those two land masses were together. Second piece of evidence are fossils. So, fossils that are found in these different rock layers kind of help us to figure out that these plants or animals lived in a similar place. And I don't mean, hey, there's one fossil that we happen to find on two continents. These are just some, and you can see where they're across several different continents. So we can start to estimate that all the land masses were together at one point. And then the last big piece of evidence is climate. This is where we find evidence of a totally different climate in a place. So we all know Antarctica is really super cold. We know that it's been super cold for a long time, but just in the past couple of months, they've actually discovered frog skeletons there. Frogs don't live in polar regions. You can't imagine like a penguin and a frog hanging out together. So if frogs lived on Antarctica at one point, it lets us know that Antarctica must have been warmer at some point in Earth's history, which means it must have been located closer to the equator, because that's really the only thing that would make it significantly warmer. So those land masses have been shifting around on Earth throughout the whole history. Why have they shifted? How do we know that they've shifted? That's in the next lesson.